All right, so what kind of alcohol are we going to get for the first one? It's going to be a secondary alcohol, right? Ketone plus reductant is always going to make a secondary alcohol, right? So this carbon here is this carbon here. It's bonded to two carbons already as the ketone, and you're adding a hydrogen, so it's going to be a secondary alcohol. What about for the next one? What kind of alcohol am I going to get there? It's bonded to the ketone, the carbon of the ketone is bonded to two carbons, and then I'm adding a third carbon with my organometallic reagent. So what kind of alcohol will I get? Adding a third carbon, carbon number 3. Tertiary. So the last one here, what kind of alcohol am I going to get? It's bonded to one carbon, and I'm adding a hydrogen. So it's going to stay bonded to one carbon. Primary. It's like pulling teeth. It's like deep down you know, but you're like, I'm not going to let them know I know it. So what kind of alcohol am I going to get for the top one here? Secondary. Right, so this here ends up bonded to this carbon here. For the next one, tertiary, right? Ketone plus organometallic, always tertiary alcohol. So this and then this get bonded together. Same thing down here, here, and here get bonded together. So it's going to be another tertiary alcohol. Red dot. blue dot. Fair. So kind of one of the last things we did last class was we looked at the 3 different types of organometallic reagents that we had. Right, so we said we have organolithium, organosodium, and then Grignard reagents. I wanted to take a second and talk about how we synthesize these. Right. I think the easiest ones to make or to understand are Grignard reagents. So we'll start with those. You take your alkyl halide, you add magnesium metal. So if I remember to put it, right, the little 0 up here, this means it's in the 0 oxidation state. Right, it's just the metal, right? Just like you'd go grab like a piece of iron, you have a piece of magnesium. Should point out that X here can be chlorine, bromine, or iodide. No fluorine. What the magnesium does is the magnesium just inserts itself in between the carbon halogen bond. Right? You always want to remember when you do a Grignard reagent that whatever the halide is you started with, it always matches the halide that's on the magnesium, right? So if you start out with an alkyl bromide, you're going to end up with a Grignard reagent that is MgBr. Okay. And I think I pointed this out again in last class. Magnesium is +2 because it's in that second column of the periodic table. So that's why it keeps the halide, is because it needs 2 -1 ligands to make it the complex neutral. So the halide is -1, and the carbon group is -1. So you have those 2 -1s to balance out the +2 that is the magnesium. So this works pretty much with any halide. It can be on an sp2 carbon, it can be on an sp3 carbon. If I don't put the 0 or you don't see the 0 there, just assume it's in the 0 oxidation state. So if I just put like Mg, or later on if I just put lithium, just assume it's the metal. Okay. So part of why it's important to remember that the halide always matches, right, is what if you had a situation where you were given like this. It's like, okay, the product was methyl magnesium bromide, was this Grignard reagent. What did you start with? You started with an alkyl bromide, right? So that's why it's important to remember that you always have your halide in your alkyl halide and in your Grignard reagent match. So that can tell you what your starting material was. So just think about it as your magnesium just stuffs itself between the carbon halide bond. Fair enough? Organolithium and sodiums are basically made the same way. We mostly use organolithium, so I'm just going to use organolithiums for the examples, but you can kind of swap sodium in. So you have your halide, again, chlorine, bromine, or iodide. You have your lithium metal. And now lithium can only be +1, right? So what ends up happening is that you get one lithium just exchanges with the halide, right? Just replaces the halide with the lithium. But you need a second lithium to be the counter ion for the halide. So for the most part, we're just going to put like lithium, but in actuality, it takes two lithiums to kind of balance everything out. Organic chemists are really bad with coefficients, so we're just going to put lithium. You just basically throw a chunk of metal in there, and when it dissolves, you're like, oh, reaction's done, moving on. Right, so you can just, again, kind of like the magnesium, right? Kind of any halide is going to work. And again, if I don't put the 0, just assume it is in the 0 oxidation state if there's nothing else on the lithium. You don't need to draw the salt, right? Because general rule of thumb is if it's water soluble, organic chemists don't care, right? So you don't need to draw the salt. So we can do this lithium halogen exchange where the lithium will just replace the halide, or we can do this through deprotonation. Right, which we've seen before, right? So you have a terminal alkyne, and you add N-butyl lithium, right? N-butyl lithium acts as a base. Doop, doop, doo. And it can remove the hydrogen at the end of the alkyne and will make an organolithium. You do the N-butyl lithium, and the other way we saw to do it, one of the other ways is like with something like LDA. Right, LDA was lithium diisopropylamide. Right, just another strong base that can do that same thing. So far, so good. So now you can do stuff like this. Right, where you can do a little synthesis, you can look at your product and go like, okay, these 3 carbons here probably came from those 3 carbons there, right? And then the rest of this came from another molecule that I added those 3 carbons to. And it's a tertiary alcohol. So how do you know how to make tertiary alcohols? An organometallic adding to a what? We literally, not H plus. We literally just did this. We opened the class on this. To a ketone, right? You add an organometallic to a ketone. So more than likely, right? the stuff in the green box, or the green circle, was a ketone. So right, the then H plus, that is to just get rid of the O minus that you have right after the reaction. So we need to, so then B must be some organometallic. You can pick one. I'm going to pick a Grignard reagent because I have the pen, right? So that would mean that A would be magnesium, right? So you're like, okay, I could take my organohalide, add magnesium to it. I can make an organometallic, and then I can add a ketone or aldehyde to it. In this case, a ketone to make my alcohol product. Fair. All right, so we have all these ways to make alcohols. So what can we do with them now that we can make them? Someone in the first class was like, drink them. And I was like, you have a very narrow window. 2 carbons in an OH, you can drink it. 1 carbon in the OH, you can drink it, but then you go blind. 3 carbons in an OH, you can drink it, but it doesn't really do anything beneficial for you, probably bad for you. Like, very fine window. There's only 1 alcohol you can drink and not have bad things happen. There might be 0 alcohols you can drink and not have bad things happen. The number of friends I had wake up and go like, where's my fill in the blank thing? My phone, my shoe, very high. Why do I have, from an old phone, why do I have a keypad bruised into my thigh? It's like, well, you rode a shopping cart and then it fell over and you fell on your phone. I don't remember any of that. Interesting, yes. All right, so alcohol reactions. I break alcohol reactions into kind of 2 big categories. Right? So I have nucleophilic reactions where the lone pair on the oxygen adds to an electrophile. And what ends up happening in this reaction is your oxygen becomes a good leaving group. So you have your oxygen react with something, your oxygen becomes a good leaving group, and then usually there is then a subsequent substitution reaction where you then knock the oxygen off with some nucleophile. Right? And then we have oxidation reactions. So in oxidation reactions, your alcohol is going to become an aldehyde, a ketone, or a carboxylic acid. Mechanistically, they kind of like share some steps, but kind of your end product changes pretty dramatically. So we're going to start with the nucleophilic reactions, and then we'll get to the oxidations a little bit later. All right. So if you remember from organic 1, hydroxide is a poor leaving group. right? We can't have hydroxide be pushed off a molecule. Right? We can't do this reaction. We can't say, hey, nucleophile, push hydroxide off of this molecule, right? Because hydroxide is just too bad of a leaving group. You can't do it. There's not a nucleophile strong enough to push hydroxide off your molecule. So what we have to do, if we want to turn our alcohol into anything else, right, we need to find a way to turn the OH into a good leaving group. Right? So we can do this, but we have to dress up the oxygen first so it can be pushed off the molecule, so it can become a good leaving group. And there's a few ways to do this. The first way is kind of the undergrad solution to most organic chemistry problems, which is just throw some acid at it and see what happens. Right? So first we can do is add acid. So I'm going to break this down into primary alcohols and then secondary and tertiary alcohols because the mechanism changes a little bit. So for primary alcohols, you have your alcohol, you add HX, where X is bromine or iodide, and you'll be able to replace the OH with the halide and make water. So the mechanism for this, right, you've got your alcohol and your acid. The lone pair on your oxygen is able to reach out and grab a proton off of your acid, and then electrons get pushed onto your halide. Right, and this is going to now give you a good leaving group. Now I have water hanging off of my molecule, right? So now this is a good leaving group. And now I can use the X minus that I made, my halide, to add to the carbon that has the water hanging off of it, push electrons over, and that's going to make my alkyl halide plus water. So this step here, after I make the water, this is an SN2-like mechanism, right? My halide is pushing my leaving group off in a single step, right? So this works for bromine and iodide. Chlorine is conspicuously absent, right? So how does this work for chlorine? Chloride is a worse nucleophile. So to make a primary alcohol leave and become a chlorine, you use HCl and zinc chloride, and that'll get you your alkyl halide. The mechanism here is a little bit different because we have the zinc in there. Right, so you have your alcohol, it adds to the zinc, kicks off a chlorine. Now my Cl minus adds, pushes off, so this is our good leaving group. Makes our alkyl halide plus this zinc complex, but with HCl, that becomes zinc chloride again plus water. So the reason the zinc's in there is the zinc pulls on the oxygen harder than hydrogen does. So basically, the zinc is pulling more electrons towards itself, so it's weakening that carbon-oxygen bond so that the chloride's able to push the oxygen off, so the chloride can break that carbon-oxygen bond. If it's just a hydrogen, that carbon-oxygen bond is not weak enough for Cl minus to break that bond and displace the leaving group. So we have to add zinc to make that bond weaker. So I kind of can't change how good of a nucleophile Cl minus is, but what I can do is I can make the electrophile better. So for both these reactions, so for the either just acid or HCl and zinc chloride, right, we don't see any eliminations because these are with primary halides and because the halides themselves are bad bases. So we almost always see just displacement. Right. This is all easy money, right? You want like as many of these as I'm willing to put on the exam, right? Because you're just saying, oh, cool. Wherever the OH is, I'm just going to put whatever halide is over the arrow in its place. So as long as we can count, we are good. 1, 2, 3, 4. I'm from West Virginia. It's a struggle, right? But 4 and 4, we're good. Here, I just need to make my OH a Cl. Make my OH a Br. Easy money. 50 of these, call it an exam. Everyone gets 100. All right. Now, when we have secondary and tertiary alcohols, the overall transformation is the same. The mechanism just changes a little bit. So let's look at this for secondary and tertiary alcohols. Right? What we're doing, the overall transformation doesn't change, right? We're like, hey, HX, here X gets to be chlorine, bromine, or iodide. We get our halide, plus we make water again. So what we're doing doesn't change, how we get there does. So the mechanism here is more of an SN1 type mechanism, right? So first step stays the same, right? My lone pair on my oxygen grabs a hydrogen, kicks electrons over onto the halide. Right now, because I'm using a secondary or a tertiary alcohol, before the halide has a chance to try to add and push the water off, the water can just leave, right? Make a carbocation plus water. Right now my halide adds to that. to get the product. So here, right, we've got an SN1 mechanism, right? Leaving group leaves, makes a carbocation, then the nucleophile adds. So we change our mechanism ever so slightly. But again, for the most part, these are also easy money. Sure. I knew as soon as I switched it, I want to touch too fast. Sure, no problem. Okay. A little more space. For the most part, these are still just wherever your OH was, put the halide in its place. But there is the complicating factor of we go through a carbocation, which means there could be carbocation rearrangements. So you just have to be mindful of when you make a secondary carbocation, you need to look at it and say, can I rearrange this carbocation? And the answer is yes, yes you can. So once you do the rearrangement, now this is what your I minus will add to. And we'll give you the product. So you just have to be, in the back of your head, you have to remember, oh yeah, carbocation, I can do a carbocation rearrangement. That doesn't change. But for I don't know, let's say 90 to 95% of these, you're just going to be wherever my alcohol was, I'm just going to put a halide in its place and my work will be done. Fair? Now, let's say you had this alcohol and you added HBr to it. Right? There are now two functional groups in this molecule that can react with HBr, right? I can react with my alcohol like we've been doing and make it a bromine. But I could also react with the double bond and make an alkyl halide and keep my alcohol. Or probably the easiest product to get is I react with both of them. The reason I say it's the easiest one is if you just add a whole bunch of acid, it'll just react with everything, right? So it's really hard for you to only make, let's say, this product, right? Because there's two functional groups that can both react with HBr. And like we've said, reagents are dumb. You can't say, hey, HBr, today, ignore the double bond. Just focus on the alcohol. And HBr is like a toddler. It's like, I do what I want, right? So we can't use HBr for something like this because there's multiple functional groups. We need to pick reagents that can only react with the alcohol and ignore the double bond. right? So if answer one was throw some acid on it, this one I'm going to say is add some phosphorus, right? So we can turn our alcohols into halides by using phosphorus-containing reagents. So alcohol to bromine. Be phosphorus tribromide and pyridine. So PYR is the abbreviation for pyridine, right? And that's going to turn your alcohol into a bromide. This reagent only is interested in alcohols. So going back to our little example that got us here, it's only going to react with the alcohol and it's not going to react with the double bond. So how does this work? So we'll take our simple example here. Great, so I have my lone pair of my oxygen. I've got this phosphorus that has 3 electron withdrawing groups around it. So I'm able to add to that phosphorus, take off my halogen. Now, we touched on this when we talked about alcohol as a weak acid. We said that weak acids and weak bases can't react together, right? Pyridine is a weak base. I'm going to kind of go down, right? So pyridine can't remove the proton from the alcohol, from, in this case, what, 1-propanol. It can't remove that alcohol. It can't remove that hydrogen. But after the oxygen adds to the phosphorus and becomes positive, this hydrogen is way more acidic now. It goes from having a pKa of like 16 to I think a pKa of like -1. So it's 10 to the 17 times more acidic than it was just as the alcohol. So at that point, that's where your base comes in to grab that proton. It doesn't take the proton off the alcohol. It has to wait for the alcohol to react with something and become more acidic. Now at that point, you end up making this. This is your good leaving group. Right, so you've turned your oxygen into this good leaving group. In the step before, you made a Br minus, right? So now your Br minus can add to the carbon that has the oxygen on it. Kick those electrons onto the oxygen. And there you go. At no point do you make anything that can react with a double bond, right? I never make any HBr. I never make any like strong acid really. So nothing here can react with a double bond. So this only reacts with the alcohol. So if I want to make chlorines, I have the exact same reaction here. All I'm doing is swapping bromines for chlorines, but everything else is exactly the same. And there's one other reagent you can use for chlorine that you can't use for bromine. Here's where we kind of break away from phosphorus. SOCl2 impurity. So now we have a sulfur involved. So SOCl2 looks like this. So it's a sulfur double bonded to an oxygen that has two chlorines coming off of it, and this is called thionyl chloride. We will use it a few more times in the semester. I want to go over the mechanism of how this works, because it's a good starting point for some of the other mechanisms we have with it. So I'm just going to redraw this. SOCl2 impurity. So much like the phosphorus, I've got this sulfur with 3 electron withdrawing groups around it. So my oxygen will add to the sulfur, kick off a chlorine. Plus some of my oxygen there, sorry. My lone pair will grab the hydrogen, push electrons down onto the oxygen. So basically the exact same thing we did with the phosphorus mechanism. And that's going to get us to here. This is our good leaving group. So now the chlorine that you generated when you added to the sulfur, that can come in, add to this oxygen, push electrons onto the oxygen. And now this anion that we made falls apart to make SO2 and Cl-. And you'll know this reaction works because SO2 smells like rotten eggs. If your lab stinks, it worked. So I do it this way, and I draw the kind of the pushing off of the sulfur containing group, the leaving group, and then it turning into SO2 as a stepwise mechanism because it kind of has less arrows. Your homework does it all in a single step, and I want to show you that. It's a little more, there's a few more arrows going on, but it's effectively the same thing. So what your homework is going to want you to do is have the chlorine add to the carbon with the oxygen. These electrons come here and then push the chlorine out all in a single step. I kind of break it down stepwise so it's a little easier to see, but they have it go this way. This is probably more correct, but I just think it's a little more complicated, so I do it the other way. So far, so good? All right. That is, I do believe, class for the day. No one has any questions or anything. So I will see you guys next time.